This begins Making Sense of Statistics, Section 7, Shapes of Distributions. So the shape of a distribution of a set of scores can be seen by examining what we call a frequency distribution, which is a table that shows how many participants have each score. So considering a frequency distribution, as you see below, the frequency, the lowercase f italicized, which is the number of participants, and the score, which is represented by X, is shown. So if we look at the table, it indicates that most of the participants, if you look at the frequency, are near the middle of the distribution with a score of 19 or somewhere around 19, and that the participants are spread out on either side, both sides of the middle, with the frequencies tapering off at the end, whether it's 22 or 15. So in this slide, the shape of a distribution is more clear when examining a frequency polygon, which is a figure that shows also how many participants have each score. Now, this is the same data that was shown on the previous page, and the frequency distribution showed that 3 participants have a score of 21. So the same information is displayed in the frequency polygon, where you can see that 3 participants had a score of 21. The high point in the polygon shows where most of the participants were clustered, and the previous table did indicate that that was near a score of 19. And if you look at the tapering off, it also illustrates how spread out the participants are around the middle. Now, when we are talking about participants, with a lot of participants, the shape of the polygon can become smoother and then is referred to as a curve. The most important shape is that of a normal curve, which is also called a bell-shaped curve or a normal distribution. So you can see that in figure 7.2. Either on page 32 in your textbook or on this slide. So the normal curve is important for 2 reasons. First of all, it is a shape often found in nature. So, for example, the heights of women in large populations are normally distributed. So there are small numbers of very short women, which is why the curve is low on the left. And many women are about average height, which is why the curve is high in the middle, and small numbers of very tall women. So, we can also look at it from a different example, also using a normal curve. The average rainfall in Los Angeles over the last 110 years has been approximately normal. There have been a few small years where there was extremely little rain, with many years about average, and a small number with a great deal of rainfall. So another reason the normal curve is important is that it is also used as a basis for many of the inferential statistics covered in Part D of the textbook. Now, some distributions are skewed. For instance, if we look at income, the income distribution for a large population, in all likelihood, you will find out that it has a positive skew, that it is skewed to the right. And so if you look at figure 7.3 on page 33 in your textbook, You'll see an example of that, and I have that here as well. Positive skew is skewed to the right. The curve drops off dramatically to the right, which forms a long tail pointing to the right, indicating a positive skew. The long tail is created from income by these small numbers of individuals with very high income. So skewed distributions are actually named for their tails. So if the tail goes to the right, then it is a positive skew. And on a number line, positive numbers are to the right, which then will also help you think about the term positive skew being used to describe a skewed distribution in which there is a long tail pointing to the right. But if you'll notice, there is no tail pointing to the left. Now, if you look at a negative skew, the long tail pointing to the left, a distribution is said to have a negative skew or skewed to the left. So a negative skew might be found in a large population of individuals who are tested on skills in which they have been thoroughly trained. So, for example, if a researcher tests a large population of recent nursing school graduates on nursing skills, a distribution with a negative skew should emerge. And what that means is there are a large number of graduates with high scores. But there should be a long tail pointing to the left, showing that a small number of nurses, for one reason or another, such as maybe being ill on the first day the test was given, did not perform well on the test. So a skewed distribution, a negative skew, the distribution is skewed to the left. In a bimodal distribution, there are two high points. So you can see the arrows point to the two humps. This is called a bimodal distribution. Now, bimodal distributions are very rare in research. The two curves, the two high points, do not have to be equal in height. A lot of times curves such as this might emerge when human intervention or a rare event has changed the composition of a population. For example, if there's a civil war in a country where it costs the lives of many young adults, the age distribution after the war might be bimodal with a dip in the middle. Bimodal distributions are less frequent than other types of curves in research. Now, the shapes of distributions have important implication for basically determining which average to compute, and that topic will be discussed in the next two sections of the textbook.